In this video, we're going to look at a couple of FP1 exam questions from Chapter 7 on series. The first one we'll do is FP1 October 2020, question 4, which is like this. And then I will do FP1 from June 2018. This is the GCE version of the paper, question 4. This one is a little bit more difficult, so we'll get to that in a moment. Okay, in the first question, we have to use the standard results for the sum of squares and the sum of natural numbers to show that the sum of 2n minus 1 squared is equal to 1/3 n 4n squared minus 1. And in part B, it says find the exact value of the sum of the squares of the odd numbers between 200 and 500. So we'll need to see how we can use our series to find that value. So we'll start with part A. First thing we will do is we are going to open up this bracket so that we can actually use the formulae that we know. So we will have the sum from 1 to n. It's going to be 4r squared minus 4r plus 1. That's the sum we are looking for. And we can break this up. We can break this up into 4 times the sum of squares minus 4 times the sum of the natural numbers from 1 to n. And this will be plus the sum from 1 to n of 1. We now bring in the formula that we know, or that we get from the formula book. So we'll have 4, and it will be times 1/6 n plus 1 2n plus 1. This one will be 4, and it will be times 1/2 n plus 1. And the last term there will be n. And at this point, we should look at what we are trying to form. We see there's a common factor of n to be taken out, which should be easy enough for us to do. But we've also got a common factor of 1/3. And perhaps that's less obvious where that comes from. But we are going to force this 1/3 n out as a factor and see what is left. So this first term is 4/6. That is 2/3. So we are going to force out 1/3 n from that. I'm going to put a big square bracket. This is 2/3, so we will be left with 2. And the n has come out, so we've got n plus 1, 2n plus 1. Left in the bracket. This one is 4 divided by 2, which is 2. We're pulling out 1/3, so we need to effectively multiply this by 3, so that will become 6. The n is out to the front, so n plus 1 remains. And in this one, we're taking out an n. We're also taking out 1/3, so we need to multiply by 3, and what's left will be 3. So that step can be quite tricky. So it's important to make sure you understand that. Okay, from here, it's going to be a case of tidying up all of this stuff in the bracket. So let's see what happens. 1/3 n. If we open all of this up, we will get 4n squared plus 6n plus 2 minus 6n minus 6 plus 3. And that gives us 1/3 n. That and that will disappear. 4n squared is left. We've got 2 minus 6 plus 3. That is minus 1. That is what we were looking for. So that is part A done. We've proved the formula that we were supposed to. Right, in part B, it says hence, meaning use what you've just done before. Find the exact value of the sum of the squares of the odd numbers. Okay, so how does this relate to odd numbers? Well, quite often when we describe odd numbers, we use 2n plus 1 or 2n minus 1. In this case, we have 2r minus 1 squared, and that's the sum of the squares. So this makes sense. So we want it to be the odd numbers between 200. So the first one we need it needs to be when 2r minus 1 equals, well, the first odd number above 200 would be 201. So we need to make 2r minus 1 equal to 201. What value of r does that give us? Well, 2r would be 202, so r would be 101. So we will start our count at r equals 101. At the top end, we will have 2r minus 1, and we need that to be equal to, it's going to be 499. That will be the last odd number before we reach 500. So if we solve for r again, we'll have 500 for 2r, and so r is going to be 250. So we need to interpret this sentence and figure out what our summation limits are going to be. From here, we can say that we are going to find r equals 101 up to 250 to r minus 1 squared. That's what we want. That is the summation for the sum of the squares of odd numbers between 200 and 500. Okay, now we know how to do this. We've already made a formula. So this would be the sum from 1 to 250 of 2r minus 1 squared minus the sum from 1 to, it's going to be 1 less than the 101, 2r minus 1 squared. And now we will use the formula that we just made. So we will have 1/3 times 250. It's going to be 4 times 250 squared minus 1. And we're going to subtract the other term, minus 1/3 times 100 times 2 times 100 squared minus 1. If we stick that into the calculator, we will get 19,499,950. And we are done. So there is our first question. That's what it should look like. That's what the working out ought to look like as well. Everything's set out nice and clear. You can check this value on your calculator, and I would recommend, if you have this option available on your calculator, you always do this. If you have this option, I would recommend you do this. We will use the summation button on our calculator. We will put a bracket, and it was 2. We have to use x minus 1. I have to use x in this calculator. Some calculators let you use any letter you want. And it was between 101 and 250. And if we let that calculate, we see indeed the answer was 19,499,950. So it's always worth checking to make sure that your answer is actually correct. Okay, if we move on to the second question. This one is a little bit more tricky. Again, it says use the standard results for the sum of the natural numbers and sum of squares to show that for all positive integers n, the sum of r squared minus r minus 8 is equal to this thing. And we've got the constant a, which is a positive integer, to be determined. Then in part B, we have to state the value, the positive value of n that satisfies this sum equal to 0. So hopefully that will be clear by the time we've found A. And in part C, we are then given this extended sum. We've got an extra term in here now that we need to deal with. We're told it's 3 to 17. The total is 6710, and we have to find the exact value of K. Let's try. Okay, so part A then, we use our standard results. We've got to find the sum of r squared minus the sum of r minus 8 times the sum of 1. So we'll start off with this. Let's see. We put the numbers in, we get 1, 6, n plus 1, 2n plus 1. That is the sum of squares. Minus, we've got 1/2 n plus 1. That's the sum of the natural numbers. Minus 8n. What have we got here? It's a third at the front, so we're going to try and force out this factor of a third to try and put it into the right form. So let's force out a 1/3 and an n. Yeah, each term has an n, so that can be taken out as a factor as well. Let's see what's left. We pull out a third when it's not necessarily there. What's left? Well, we have to multiply by 3, so that's going to be 3/6, so we'll be left with 1/2. And if you're not sure about that, just check what happens when you multiply back in. You actually do get your 1/6. So it's going to be 1/2 n plus 1, 2n plus 1. We forced out a third when there was a half there, so that will be again multiplied by 3, so it needs to be 3/2. The n has gone out to the front, so we've got n plus 1. And in the last term, we're forcing out a third, so that's going to become 24, and the n has gone to the front. Okay, this looks a bit weird, but let's see what happens. Hopefully a lot of the fractions are going to cancel out. So we've got 1/3 n. Let's see, if we open all of this up, we will get 1/2 2n squared plus 3n plus 1. I guess we've got minus that, minus 3/2n, minus 3/2, and the minus 24. Let's open up this last bracket. So that's n squared plus 3/2n plus 1/2. And now we see that some of this is going to cancel out. We can now cancel those two, and we'll combine everything that's left and see what we get. We should have n squared. We've got 1/2 minus 3/2, that's minus 1, minus 24 gives us minus 25. And suddenly this thing here becomes clear. We now are left with a difference of 2 squares. So we can now say that this is n minus 5, n plus 5. So that is the end of part A. So where a is a positive integer to be determined, so we know that a equals 5. Okay, part B, it says, hence state the positive value of n that satisfies this thing equal to 0. So if we replace the summation with its formula now, we get this. This has to be equal to 0, so we have 3 options. We can say n equals 0, n equals 5, or n equals minus 5. It says state the positive value for n. So the answer we require is n equals 5, and those two we can get rid of. Okay, so 1 point for doing that. In part C, let's see what we get. In part C, I'm going to write this down here. Right, we've now got this extra term. We see that compared to what we had before, we now have this kr³ term at the start, plus r squared minus r minus 8. Okay, so we're going to have to deal with the kr³. We're also going to have to deal with the fact that the sum now starts from 3. Let's do the kr³ first of all. Well, we know that if it were 1 to n kr³, okay, we could take the k to the front, and it would become k over 4 n squared n plus 1 squared. Right, so now we're going to try and put this all together. We are going to have, if we had r equals 1 to 17 of kr cubed plus r squared minus r minus 8. If it were 1 on the bottom, we would now have k over 4 n squared, n plus 1 squared. And then we'd have the thing from before. We'd have the 1/3 n, n minus 5, n plus 5. So we've got our formula. However, just to make things even more complicated, our sum does not start at 1 anymore. It starts at 3. So we've got to deal with that as well. So remember, if we want the sum from r equals 3 to 17 of all of this, that is going to be equal to the sum from r equals 1 to 17 of all of this minus the sum from r equals 1 to 2. Remember, it's always one less than that. We want to subtract the bit that is not required. Okay, and again, the whole cubic would go in the brackets. Right, we're going to have to just put in all the numbers now and see what happens. Okay, so we've got up to 17. So we will have k over 4 times 17 squared, and then we've got 17 plus 1, or 18 squared, plus 1/3 times 17, 17 minus 5, 17 plus 5. So that will be the first bit, and then we're going to subtract the sum from 1 to 2. So we'll have k over 4, 2 squared, 2 plus 1 squared, plus 1/3 times 2, 2 minus 5, 2 plus 5, like so. And we are told that that entire thing is equal to 6,710. So all of this is going to be 6710. So at this point, it seems like we've got everything we need. We just have a pretty nasty looking calculation to do, but from that we should be able to find k. So let's work it out. The first term, if we work this out, we will get this comes to 23,409 times k, plus this is 1,496 if you put it in the calculator. We then have to subtract this term, so we've got minus, and that comes to 3 squared is 9k. And in this one, because that will be a negative term, we've got a negative at the front of the bracket times a negative. This becomes plus, and the total of that comes out to be 14. So we're nearly there. We're nearly there. We can now solve this. If we gather up all these numbers, we end up with 5,200 equals 23,400k. And from there, we can solve. We get k equals, well, it will be 5,200 divided by 23400. K equals 2/9. And as before, once we've got our answer, it's always worth using the calculator, if you can, to check this. If we think it's 2/9, then let's do this. We think it's 2/9 times x cubed. Okay. We had plus x squared minus x minus 8. And we have to check this between 3 and 17. The answer we're hoping for is 6,710. That must be the answer if the 2/9 is correct. There we go, 6,710. So that now confirms that our answer of 2/9 for k was correct. And we would now move on to the next question, knowing that we've got all the points there.